Hi everyone, welcome back to Made Everything Official. From the scorching desert heat to the frozen Arctic, Volvo machines are built to endure the harshest conditions on Earth. But even the toughest components eventually wear down, and when they do, Volvo Riemann gives them a new life. It begins with a core, a worn-out engine, gearbox, or filter, collected and sent to Volvo's core hubs. Each one is carefully inspected, and only those meeting strict quality standards move forward. The rest are recycled responsibly. At the remanufacturing plant, every core is completely disassembled, cleaned through advanced chemical processes, and freed from corrosion. Components that pass inspection are restored to a technically new state, while those that fail are replaced with brand new parts. Reassembly follows the latest engineering updates, ensuring that every remanufactured unit matches Volvo's newest specifications. Rigorous testing then simulates extreme operating conditions to confirm full performance and reliability. Finally, each engine is refinished and painted, identical in appearance, function, and quality, to a brand new part. By reusing up to 85% of the original material and saving 80% of the energy required for new manufacturing, Volvo Riemann combines durability with sustainability. Every remanufactured part meets the same technical standards and warranty as a new Volvo component, proving that engineering excellence doesn't end when a part's first life does. At Volvo Riemann, the future is rebuilt, one part at a time. The new Volvo FH is more than a truck. It's a masterpiece of engineering. Packed with more computing power than an aircraft, it connects like a smartphone, yet delivers the strength, safety, and efficiency that define Volvo. It all begins with a roll of sheet steel, the foundation of every unique Volvo truck. In the cab plant, this steel is shaped by over 340 precision presses, producing millions of components each year. Every panel is formed in multiple stages to ensure a perfect fit when the cab comes together. The assembly line is alive with more than 300 robotic arms, moving with flawless precision. Guided by advanced computer programs, each robot welds, joins, and shapes the cab, including a state-of-the-art laser welder that achieves an accuracy impossible for conventional systems. Within hours, raw steel transforms into the recognizable Volvo cab. It then enters the paint shop, one of the most environmentally optimized facilities in the world. Every surface is coated by automation, using just 4 liters of paint per cab, half of what was needed a decade ago. Next, in cab assembly, hundreds of technicians install electronic systems and interior components. Over 350 skilled hands ensure every circuit, seat, and control fits perfectly. Even the glass is bonded to the cab, improving safety and structural integrity. In just 3 days, the once flat steel sheet becomes a complete, ready-to-ship cab. Meanwhile, at the engine plant, molten metal heated to 500 degrees Celsius is cast, machined, and assembled into high-performance power units. When the cab and engine are complete, they converge at the chassis plant, where construction has already been refined through hundreds of pre-series builds tested around the world. Here, the chassis is mounted upside down for assembly, allowing engineers to work efficiently. Advanced electronics synchronize dozens of control units, the truck's nervous system, exchanging data hundreds of times per second for speed, steering, and stability. In just over 5 days, 790 screws, thousands of welds, and countless hours of precision turn raw steel and circuitry into a fully realized Volvo FH, a state-of-the-art machine weighing over 8,000 kilograms, built to conquer the road with intelligence, strength, and Scandinavian perfection. This is the Niles Simmons turnkey crankshaft manufacturing line, the latest generation of flexible production technology, built for BMW and successfully installed at the BBA plant in Shenyang, China. A masterpiece of German engineering and automation, this system transforms raw forged steel into precision crankshafts that power some of the world's most advanced engines. It begins with crankshaft blanks, heavy solid pieces of steel precisely forged to rough shape. They're automatically loaded into the line and secured for machining. Every detail from alignment to positioning is digitally controlled, ensuring the part is perfectly referenced before the first cut is made. At the rough turning stations, high-torque CNC lathes remove material to define the journals, counterweights, and bearing surfaces. These first operations are all about stability. Every movement carefully measured, every micron monitored. The entire system is synchronized through intelligent spindles and robotic handling that move in perfect rhythm, keeping the workflow continuous without human interruption. Next, the crankshaft enters fine turning and milling cells. Here, the contours are refined, oil channels and keyways are machined, and fillet radii are sculpted with extreme precision. Niles Simmons machines use multi-axis interpolation and adaptive control to compensate for tool wear and thermal expansion, guaranteeing accuracy even during long production cycles. After machining, grinding and superfinishing begin. Each main and rod journal is ground to within microns of its final dimension, producing surfaces that are mirror smooth. Special profile grinding wheels create the exact geometry required for high-speed performance, while automated coolant systems maintain temperature stability across the entire line. Then comes precision balancing. Each crankshaft is dynamically tested to detect even the slightest imbalance. Microscopic adjustments are made through drilling or material removal, ensuring that when it spins at thousands of revolutions per minute, vibration is virtually eliminated. Every process step is digitally linked. Sensors track tool condition, spindle loads, and dimensional data in real time. The system instantly communicates with quality control, creating a live production feedback loop. Robots handle transfers between stations, washing and drying parts before inspection to prevent contamination. In the inspection and verification stage, advanced measuring equipment checks concentricity, runout, and surface finish. Laser scanners and coordinate measuring machines confirm that each component meets BMW's rigorous specifications. Metallurgical tests, such as hardness and microstructure verification, ensure long-term fatigue resistance. Once certified, the crankshafts proceed to cleaning and logistics. Automated conveyors and robotic sorters move them into final packaging, ready for assembly lines across BMW's global network. Each part carries a digital ID, a complete traceability record of its origin, machining parameters, and inspection results. The entire line exemplifies the philosophy of Industry 4.0, automated intelligence, closed-loop control, and unmatched precision. Designed by the NSH Group, it combines decades of experience in crankshaft production with cutting-edge software and mechatronic integration. In the end, this system doesn't just build crankshafts. It builds reliability, efficiency, and the mechanical heartbeat of every BMW engine. From raw steel to finished perfection, Niles Simmons defines the future of precision manufacturing. In the world of precision machining, champions rise, and DMG Mori leads the pack with its 5-axis mastery. These machines combine speed, accuracy, and flexibility to transform raw material into engineering excellence. With 5 synchronized axes, every movement is controlled, every motion seamless. Complex shapes, deep pockets, and tight curves. Nothing is out of reach. The tool guides itself through contours, rotating and tilting to maintain optimal cutting angles. CNC logic handles the balance internally. Tool wear, material resistance, and thermal expansion are all adjusted on the fly. The result? Surfaces with flawless finish, perfect geometry, and resilience under stress. From aerospace parts to intricate molds, the 5-axis champions are the backbone of tomorrow's manufacturing, where freedom of motion meets uncompromising precision. Have you ever wondered how industries like aerospace, automotive, and medical manufacturing create components with such incredible precision? It all comes down to the power of CNC machining, a technology-driven process that transforms raw materials into perfectly engineered parts using computer-guided control. CNC, or Computer Numerical Control, combines precision, speed, and repeatability. It's the foundation of modern manufacturing, ensuring consistent quality, even at the highest levels of complexity. Among its many forms, CNC milling stands out. Rotating cutting tools remove material layer by layer, carving out complex 3D shapes with tight tolerances, ideal for molds, turbine housings, and engine components. Then there's CNC turning, where the workpiece itself rotates while the cutting tool remains stationary. This technique is essential for producing cylindrical parts like shafts, bushings, and threaded fittings, delivering flawless finishes and dimensional accuracy. CNC drilling takes precision even further, creating holes of all sizes, from microscopic apertures in medical devices to large industrial bores. Every hole, every edge, every depth is controlled to perfection. For ultra-hard metals, wire EDM, or electrical discharge machining, uses an electrified wire to cut with microscopic accuracy. It's the choice for aerospace alloys, molds, and tools that require extreme detail and durability. Beyond these, specialized methods like CNC laser cutting and CNC plasma cutting offer speed and versatility, slicing through metals and composites with precision and efficiency. Together, these technologies form a complete ecosystem of innovation, shaping everything from precision implants to jet engine components. In the heart of every modern device lies a marvel of human ingenuity, the microchip. A single chip can take up to half a year to produce, built from more than 100 microscopic layers, and housing billions of transistors within an area smaller than a fingertip. These tiny circuits are the brains behind our digital world. The journey begins with silicon-rich sand. Silicon is the perfect semiconductor, not quite a metal, not quite an insulator, allowing its electrical properties to be finely tuned. When combined with trace elements, it can control electrical flow with incredible precision, forming the foundation of every electronic device. To extract pure silicon, sand is heated with carbon in crucibles at extreme temperatures, separating it from oxygen. The result is 99% pure silicon, which is then refined further into a flawless single crystal called an ingot. A seed crystal is dipped into molten silicon and slowly pulled upward, growing into a large, cylindrical crystal that can weigh hundreds of kilograms. Next, the ingot is sliced into wafer-thin discs, each perfectly flat and mirror-smooth. These wafers are the canvas upon which the microchip will take shape. The larger the wafer, the more chips it can hold, from dozens to hundreds on a single slice. Inside ultra-clean rooms, where even a dust particle could destroy an entire batch, the wafers undergo deposition, forming a thin layer of silicon dioxide on the surface. Then, a photosensitive coating is applied to prepare it for one of the most critical stages, lithography. Using beams of ultraviolet light passed through a reticle, essentially the blueprint of the circuit, patterns are projected onto the wafer. Exposed regions harden, while unexposed areas are etched away by reactive gases, carving out the intricate microstructures of the chip. Each layer is then modified through doping, adding controlled amounts of elements to adjust conductivity, followed by etching and metal deposition to create the electrical pathways that connect billions of transistors together. This process is repeated over and over, sometimes hundreds of times, until the entire integrated circuit is formed. Once completed, Thin metal layers, often aluminum or copper, are laid down to carry electrical signals across the chip. The wafer is then tested, and each chip is carefully separated using diamond saws. Inside every microchip are the fundamental components of electronic life: capacitors that store energy, resistors that regulate flow, and transistors that amplify or switch signals billions of times per second. In the heart of modern manufacturing, precision meets power, and nothing embodies that better than the brilliance of laser cutting. Here, 8 high-performance laser cutting machines operate side by side, turning raw metal sheets into exact, functional art. Each system uses a concentrated beam of light, a laser so intense that it melts and vaporizes metal with surgical accuracy. Guided through mirrors and lenses, this invisible energy strikes with precision measured in microns. It slices through steel, stainless, and aluminum as though they were paper, yet every edge remains clean and true. Inside each machine, a fiber laser generator produces the beam at incredible power levels, often between 3 and 12 kilowatts. These beams travel through optical fibers to the cutting head, where autofocus lenses adjust in milliseconds to maintain perfect distance from the material's surface. Assist gases like oxygen, nitrogen, or argon are injected to blow away molten metal, preventing oxidation and ensuring flawless cuts. Across the factory, automation keeps the workflow in motion. Shuttle tables slide in fresh sheets as finished parts move out. Robotic arms and conveyors synchronize perfectly, allowing all 8 lasers to operate continuously with minimal downtime. Every motion of the cutting head is orchestrated by CNC control systems, reading digital blueprints that define each contour and hole. Accelerations are lightning fast yet vibration-free, thanks to servo motors and precision ball screws. The laser head glides effortlessly, tracing paths with repeatability finer than a human hair. High-speed sensors monitor beam intensity, focus, and nozzle height in real time. If a deviation or warping occurs, the system instantly recalibrates, ensuring quality remains uncompromised even after hours of non-stop operation. Each cut produces a fine shower of sparks, a visual symphony of light, energy, and precision. From small brackets to massive structural panels, the machines craft components destined for industries like automotive, construction, energy, and advanced manufacturing. Once the cutting is done, parts are sorted, deburred, and inspected under quality lights. Their surfaces gleam with smooth, oxidized edges, proof of the perfection achieved by light itself. This is the art of laser technology: clean, efficient, and endlessly adaptable. 8 machines, one purpose: transforming cold metal into the backbone of modern innovation. Laser cutting represents more than fabrication. It's the mastery of light, a process where science becomes beauty and precision becomes progress. Thanks for watching. Don't forget to like, share, and subscribe. More powerful machines are coming soon on Made Everything Official.